Hello there, whoever watching. This video is going to be about A-level integration. The objective of this video is to address some of the integration difficulties encountered by A-level students. The main three techniques that people study is reverse chain rule, integration by substitution, and integration by parts. And we will go through some of the common mistakes that we make. Here's a key observation. When students know what method to apply, such as by parts or substitution, these are very easy. Now, on the other hand, if the question does not specify what technique to apply for integration, that's when students tend to find those questions difficult. So, not only we need to learn what the tool does, but when to use them, such as when reverse chain rule is applicable, or partial fractions, and so on. A quick, useful exercise might be to go through these integrals and see what integration methods or strategies are applicable. We will go through these questions again after we reviewed through all the methods. Pause the video and have a think. So, let's go through the integration methods one by one, starting from reverse chain rule, then integration by substitution, and finally integration by parts. So, let's start with a simple reverse chain rule question to understand what we should look out for. Usually for reverse chain rule, we have a function when differentiated give us some other function. For the second one, we see that when we differentiate cos, we get something of the form sine. So these are good candidates for applying reverse chain rule. Now what we then do is we must guess our function. In this example, we could guess our function to be x cubed plus 1 to the power of 5. And now we need to think about what coefficient to put. Here, we see that we must drop the 5 and the 3, and therefore we need to divide by 15. We can check this by differentiating this function and see that we get back our original function over here. For the second question, we may guess our answer to be of form ln cos x. Again, we must be careful with the coefficient, and since cos x differentiate to negative sine x, we see that we must have a negative sign. So, let's summarize what we just did. Reverse chain rule is by far the most simplest integration technique, as we are simply guessing our answer. So if we have some intuition on what the answer is, then we can solve it. The key aspect of this method, however, is that it must involve some derivative, and we need to be careful that we don't make any coefficient mistakes. So, let's now do integration by substitution and prove this equation. We can suspect that we're going to use substitution as we now have a different variable. And perhaps we should define u to be x squared plus 2. Let's see where this would lead us up to. We must make sure we work out the derivative. And let's make dx a subject. Okay, well now let's try substituting these values in. When I substitute it, I get du over 2x. Now a few things. One, because we are now integrating with respect to du, we should change the limit. And the limit is based on these x values. We are asking ourselves, what is the value of u when x is 0 and root 2? And we see that the limit changes to 2 and 4. Now, let's try to simplify this expression. The problem here is that we have two different variables, and we want to make sure that our integral is now with respect to new variable u. So let's think how we can rewrite this expression x squared in terms of u. Well, that's rather simple, because we could define x squared as just u minus 2. And therefore, let's put that in. And we see that this expression is precisely what we required, and therefore we are done. Let's summarize what we just did. When we use substitution, we are changing the variables from x to say u. And when we do that, we must make sure all of the function is in the new variable u, and also the limit should change from x values to the u values correspondingly. Now, let's look at a rather annoying trick where we use trig substitution to solve questions. When do we use these trig substitution? Well, we want to use them when we think that we can exploit trig identity. So for the first example, if we try x to be sine theta, we see that the square root of 1 minus sine squared theta is just cos theta. And that's precisely the reason why trig substitution might be a good candidate here. To finish this working off, we can take the derivative of sine, which is cos theta, and therefore when we combine these two results, we get cos squared theta as required. Similarly, for the second question, we can try x to be sine squared theta. As notice again, this bottom part is going to simplify using trig identity. And perhaps because I'm turning quite lazy, I would ask the audience to finish off this calculation to show that when you use this substitution, we end up with 2 integral of sine squared theta. One quick remark is that these integrals can be solved by using double angle formula, where you use cos 2 theta and use a corresponding equation to solve it. Good luck. Last but not least, let's go through integration by parts and do the following integral. So, whenever we are dealing with integration by parts, we must specify what v and du over dx is. In this example, we are taking v to be x and du over dx as e to the x. Let's see why this is good. This last integral simplifies to dv over dx, which is 1, and u becomes e to the x. And this integral is just the integral of e to the x, which is just e to the x. Compare now what happens if we use the wrong choice. If we now swap this around and took v to be e to the x and du over dx to be x, the problem again lies on this last integral, where u is now a half x squared. The problem with this is that this integral looks much more difficult than what we started with, and therefore we've complicated the problem. So a key point is that we must identify the correct variables in order to simplify our problem at this integral stage. 2 quick remarks. Integration by parts can be applied to a rather difficult question where you need to use a trick, where we need to decompose a function in the form 1 times that function. And the other one is where we need to use integration by parts multiple times, which can be rather cumbersome. Consider the following problem where we want to integrate Linux. To do this question, we're going to write Linux as 1 times Linux and choose the appropriate variable. Here, since we do not know what the integral of Linux is, we're going to define Linux to be our v, as we do know how to differentiate Linux. We're going to call du dx to be our 1, and when we apply that, we see that the last integral is going to be dv dx, which is 1 over x, and u is going to be x. And that integral simplifies to just 1, and therefore our question is solved. Now, when do we apply this trick? This trick is often present when we are differentiating an inverse function. So things like the integral of arcsine x, arccos x, and the one which we'll see later, ln x squared. Let's look at the second trick, which is to apply by parts multiple times. So if we want to find this integral, we want to use integration by parts twice. Why? Well, we do know how to solve this integral over here. And since we got x squared here, we're probably going to use by parts twice. And here we see that we call this to be our v and this to be our du over dx. And when we integrate it the first time, we get this integral, of which we have already solved, and therefore I just plug in that expression again. So there we have it. A rather nice question based on these two tricks is the following integral. This was one of the infamous questions in the recent paper, and I would advise you to have a go at it. Pause and have a think. There are fantastic resources online, such as an online integral calculator. And what it does, as the name suggests, it will solve an integral that you provide, and it will give you a step-by-step solution. So if there are any questions that you have on this video, of course you can comment, like, share, all that crap, but you can also check it online using these calculators. So let's go through these integrals that we started with. For the first question, we showed that we want to use the substitution x equals sine theta, so that our integral becomes of the form cos squared theta. And from here, you can apply the double angle formula, and we are done. For the second question, we see that the derivative of x squared is present over here, and therefore we apply reverse chain rule. For the next question, we could again apply the substitution x equals sine theta, and you will see that this integral will simplify to sine squared theta cos squared theta. And notice that this question is exactly identical to the last question, so we'll see how we will solve that later. For the fourth question, we see that we have a product, and we can't seem to use any clever substitution, and therefore we will use parts, where we call this to be our v, as when I differentiate v, I just get 1, which makes it much easier to integrate. For the next question, we see that we already solved this question, similar question, over here. And the idea was to use double angle formula to solve the question. For the next question, we see that the derivative of sine give us cos, and therefore this is another chain rule question. For the integral sine cubed x, there's a rather nice trick where we can write sine squared as 1 minus cos squared x times sine x. And now we see that when I integrate sine x, I just get minus cos x. And the integral of sine x cos squared is rather similar to the one which we did over here, where we can apply the chain rule. Last but not least, the final integral is rather tricky. One way to solve this is to observe that sine x cos x is just a half sine 2x. And therefore we can rewrite this integral as a quarter sine squared 2x. And I'll wave my hand and say that we do know how to integrate such functions, and therefore we are done. If you have any questions, feel free to comment or email me, and also use Wolfram Alpha. Few quick remarks before ending the video. Number one, if you see any observation, start with that. Things like reverse chain rule, integration by substitution is usually quite easy. So if you spot that, go for it. Also remember that algebra is so crucial in A-level because it lets us simplify many problems that is otherwise seemingly difficult. And there's a famous phrase that good mathematicians is a lazy mathematician because often mathematicians don't want to do a lot of calculation, so they often train their intuition so that they can solve questions quickly. Alright, thanks for watching, and all the best to your exams and beyond. Good luck.